Now we're going to be talking about reversible reactions in equilibrium. So we'll get back to this diagram on another slide, but this one kind of throws it all together. I really like it. It's a good example of the dinitrogen tetroxide reaction that turns into nitrogen dioxide. But it's nice because the dinitrogen tetroxide is clear, and then as the nitrogen dioxide, NO2, starts to build up, it turns into that brown gas. So you can see a color change. And a lot of these reactions are really good because you can see color change when it happens. All right, so reversible reaction. Basically, reactants to products is what we've been doing. But this means that it can go either direction. We have a forward reaction going that direction towards the products, or you have the reverse, okay, or the backward reaction, but we call it the reverse, okay? So product to reactant. And that's why we use the double arrow here. Now, dynamic equilibrium is when you're in a closed system, okay? Obviously, if it was like, because we're talking about gases a lot of times here, if the container is open, then the gas can just escape. So it'd have to take place in a closed system. That's kind of important. Now, dynamic equilibrium is when the rates are equal to one another. You're making product just as fast as you're making reactant. It's exactly equal. When those get to be equal, and dynamic equilibrium, the word dynamic, why is it there? Because this is, it's a constant process. It looks static to us, but products are making reactants, reactants are making products at the same rate constantly. So it is, really a lot going on under at the atomic level. And here's that reaction again. Like I said, we're going to go through some of this here, showing the rate versus time graph, where the forward equals the reverse. So this is the K forward is the rate constant. So it's decreasing going forward. The rate constant of the reverse is picking up speed. Okay, and then they eventually equal each other, and that's what this dotted line here is telling you. You're at equilibrium. So as you can see the rates are equal now over here. So that's one representation of equilibrium, looking at the rates equal each other. Okay, so we're going to go ahead and take a look at a quick YouTube video.
A chemical reaction at constant temperature in a closed system is in a state of dynamic. These are constant concentrations of reactions and molecules. Consider the rest of
In the video you just saw about basically when the rates equal each other, you also have concentrations of reactants and products remaining constant at this point. So here's that dotted line again representing the equilibrium state where, initially you're starting off with reactant and its concentration starts to decline. You're making products, so their concentrations start to increase, but it eventually flattens out to a concentration amount. Now, these stay constant with time. Now, reactants are making products, products are making reactants back and forth, but these amounts stay that same amount. And it's not usually where the products equal the reactants. One side usually is more favored. In this case, the NO2 has the higher concentration, so we would say the products are favored at equilibrium. and the reactants are not favored at equilibrium in terms of the concentration amount. Now rates equal each other, and then the concentrations remain constant with time at this state of equilibrium. So that's why this example is really good. I like because it starts over here with the dotted lines. It's barely getting started here, so all you have is the reactant in, and it shows you the atomic view here, the particulate view, and it's a clear gas, okay, at this point, and dinitrogen tetroxide. As equilibrium, or as it starts to progress, you can see the dotted line here. Now it's a little bit more. So now you see some NO2 starting to pop up, and that's creating the little brown gas inside. But we're not to equilibrium just yet. Eventually it reaches the equilibrium, which shows you the ratio, and as you can see, there's 1, 2, 3 of these guys, then dinitrogen tetroxides, and then there should be double the amount here. So we have 1, 2, 3, 4, 6, 7, 8. I guess there's 8 there. But basically, at this point, really, there should be 6 represented inside there, showing at equilibrium under that particular view, those would be the relative concentrations. And of course, products are favored because you have more of the product than you do of the reactant. So you have your concentration versus time graph here, showing how the concentrations get constant and remain constant. And then you also have your rate versus time graph, showing that the rate of the forward equals the rate of the reverse. All right, so learning check real quick. Water molecules in the sealed jar, so closed system, are in a state of dynamic equilibrium because water vapor molecules, A, are condensing at the same rate that others are evaporating, B, evaporating faster than they are condensing, C, cease to form when air in the jar becomes saturated, or D, form only at high temperatures. Well, as I also showed in the video, they're finally getting to that same rate here. So A would be the correct choice. Now for equilibrium expressions. Equilibrium expressions follow this particular equation. It's called the law of mass action. You don't really need to know that, but this is giving you a quantitative measurement of how far the reaction proceeds, how much product is actually made. So it gives you that mathematical representation. Now the way to write this is you have your products, your C and D concentration of your products raised to the power of their coefficients. So like here, L is that coefficient, molar coefficient, and then M would be the molar coefficient for D. We use the brackets, of course, because we're denoting concentration here. But it's always products over reactants. So K is always products over reactants. But we take the individual concentrations, raise them to the power, and then the reactant concentrations raised to the power of their coefficients go on the bottom. So simple formula here, and then we calculate this K value. And this K value is going to provide us information as to where the equilibrium position is. If the products number, the numerator here is higher, obviously, K would be greater than 1. If the reactant number here on the bottom is greater in the denominator, then the K is going to be less than 1. So that's kind of our reference point. We're going to look at that. Now, it differs for every reaction, KEQ or K, and it's constant it's constant when you keep the temperature constant. The only thing that can change an equilibrium constant or K is if temperature changes. If temperature changes, you affect the kinetics of the speed of the reaction because the molecules are moving faster if you increase temperature. So then you will also change the K value, or this ratio between products over reactants. Now, which chemical species have concentrations? We need to know what we can actually use in our equilibrium expression. Remember, concentration is a measure of molarity, which is moles per liter. Well, gases and solutions, AQ and gases, of course, these guys have concentrations that are going to change, okay? These ones, we would say the concentrations can change. However, looking at stuff that doesn't really have a changing concentration, we would not want to include into the reaction. So which ones would we exclude are the ones that where their concentrations don't relatively change. So that would be pure substances like solids and liquids, pure substances that are not mixtures, okay? their concentrations do remain constant. And let me try to explain this to you because it's kind of a difficult thing to visualize. But so we're talking about a heterogeneous equilibrium. So that's if like you have a gas reactant plus a liquid reactant giving you, a solid product or something like that, where they're not all in the same phases. That's what heterogeneous equilibrium means. So it does not depend on the solids or liquids amounts. Why? Because the standard state of solids is their molar density, which is pretty much their concentration. Now, if you take away some of the particles, you also take away that same amount of space. So really, it stays at a constant value. The concentration does not change. You can take away some of the particles or compressed particles of a gas and alter the concentrations that way. But for solids and liquids, the concentrations remain constant. So if we're looking at practicing writing out an equilibrium expression, this is one task that you're going to have to do in the practice here. You're going to write out an equilibrium expression. So looking here at this balanced equation, you write KEQ. Now, we have to do products over reactants. So the concentration of our carbon dioxide, which happens to be our first product, we're going to raise it to the third power because of the molar ratio is 3. Over here, concentration of water, and we're going to include it because it's gaseous water, water vapor, raise it to the 4th power here. Then we look to our reactants, propane, write that here, the concentration of propane, remember brackets mean concentration. Now this is an understood one, so you don't really have to put the power there. And then we have gaseous oxygen as well, so we're going to include that, and it's to the 5th power. So that's how the KEQ expression would look for the combustion of propane reaction here. Like so. So you're going to have to write out the expression. This one is an example of the hetero equilibrium, because if you look, we have gas, we have liquid, and we have AQ. So we have different phases here. Not everything's a gas like it was in practice number 1. So KEQ, once again, I'm going to look at my products. I have AQ and AQ. They both have concentrations that change, so they're going to be included. So I put in here ammonium and hydroxide. They both have, a coefficient of 1 here, so I don't have to put the 1 as the power. Then I look here. I'm not going to include the water. Why? Because it's a liquid. That's a pure substance, concentration not changing. And then on the bottom, I would put the ammonia gas in here because obviously, yes, it's a gas and you can change the concentration of that. Once again, the molar ratio is 1, so you don't have to put the power there. But this would be the KEQ expression for this. This is actually a base reacting with water, forming ammonium and hydroxide. One of those Bronsted-Lowry base type reactions you see here. It's in equilibrium with water, where only partially ionizes, about less than 5% over here partially ionizes, and it establishes an equilibrium position. So yes, that would be how you would write out the KEQ for, or the equilibrium expression for practice 2 here. Now, we use them to determine how the reaction proceeds. We get that ratio so we know which side is favored. Is it the products that are favored, or is it the reactants that are favored at equilibrium? So if K is greater than 1, the reaction favors product formation. You have more products than you do of reactants at equilibrium. That constant concentrations, there's more products. Now, K or KEQ is less than 1, the reaction favors the reactant side. Once again, in the ratio, the denominator is bigger, so K is less than 1. That means you have more reactants than you do have products at equilibrium, those constant concentrations. All right, so you'll be given an example like this where you have the concentrations at equilibrium, NO2, NO, O2. So basically what you do is you write out the expression first. So we do products over reactants. So I have concentration of NO times concentration of oxygen over concentration of NO2 raised to the 2nd power. These two both have coefficients of 2. Then all you have to do is plug in and chug, basically. Plug in the values. So NO, 0.160 raised to the 2nd power, and here's our oxygen, 0.080 over RNO2, which is 1.20 raised to the second power. Then all you have to do is plug it in your calculator and calculate it out. And once you do that, KEQ equals this value. And going on sig figs, this one has 2, so we're going to go with 2 sig figs here. Now, Ks do not have units, so it's just a value. As you can see, you could write this as scientific notation as well, and you'll notice that KEQ is less than 1. If KEQ is less than 1, that means that the reactants are favored at equilibrium. That means there's the higher concentration of reactants remaining constant than there are products at equilibrium. Reactants are favored here. So that's one example. Another example here, different reaction. We have sulfur dioxide plus oxygen giving us sulfur trioxide here. Once again, spend a moment to write out your expression. Raise to the second power, here's our product. Okay, got that down. First reactant, raised to the second power, and then our second reactant is oxygen here. Then you just plug in the numbers. All right, so SO3 is right here, so 0.78 raised to the second power over 0.44 raised to the second power times our oxygen 0.22. And once you solve this, you put it in your calculator, you'll end up with KEQ being 14. Now that means KEQ is greater than 1. So the products are favored. Sorry, going back here. Products are favored at equilibrium. So take a moment to see here now, KEQ being greater than 1, products are favored at equilibrium. Now, if a stress is applied to a system at equilibrium, the system proceeds in the direction that will relieve the stress. This is Le Chatelier's principle, and he's a French guy. And basically what happens is you apply a stress to the system, and it's going to move in a direction to reestablish equilibrium. Go back to the K equals products over reactants. It wants to reestablish this ratio. So it's going to keep going back and forth until it gets back to that K ratio value, that given amount of product over reactant. You can use Le Chatelier's principle to predict how changes in concentration, temperature, and pressure are going to affect equilibrium. So keep in mind here, these factors are what we're going to be looking at that are going to be the stresses that can be applied to the system. So I have a short little video here for you to watch, so hold on one second. process, which we'll look at as well, produces ammonia, which is definitely needed in our fertilizer, and it's produced, industrially because of that factor. And like I said, they manipulated the reaction to be at a certain temperature and pressure to yield the most ammonia. Because it is a equilibrium reaction, it doesn't go to completion. It's not like you're just going to produce lots of ammonia, and we want the biggest yield for our amount of reactants and the resources being put into the reaction. So they manipulate it at the temperature and the pressure to make sure it cranks out a lot of ammonia to put in the fertilizer. All right, so here, looking at some changes here. If you're changing concentrations, increasing them, increasing concentrations. Increasing concentrations of reactants produces more products. So increase this, it's going to shift to the right and produce more product, basically. I'm adding to the left side, it's going to proceed to the right side. Same thing here if I'm adding to the products. If I add over here to the SO3, it's going to shift to the left, produce more reactants to get back to equilibrium, to get back to this K equals P over R ratio of the products over reactants. It wants to reestablish this ratio. So keep that in mind when you're looking at, you add in, it's going to shift the other direction, basically is what's going to happen. Now, this particular one, increasing the concentration of CO, we know we're adding it here, it's going to shift to the right. We're going to produce more methane, more water. In this case, it's a gas, so we include it. What I want to point out that when you add in CO, yes, this one increases. This one goes up. But, and so do these two, because you're shifting to the right, they're initially going to increase in order to get back to equilibrium. What's going to happen to your H2, though? Well, you add in CO, this H2 is going to be consumed since we're pushing it to the right and going to make more product. So the actual concentration of the H2 decreases because you're consuming it to produce more of the methane and the water vapor over here to the right. Now, removing water, so let's look at this, where if we're going to take out water, we're going to decrease the concentration of the water vapor here. Removing it means it'll shift to the right, okay, because it'll want to make more water and replace the water that has been removed. So removing things goes to the same side from which you removed it from to reestablish that equilibrium. That also means that both of these concentrations, like the concentration of CO, that one's going to decrease because it's going to shift to the right, and so will the concentration of the hydrogen will decrease, but the concentration of the methane in this case would increase because you're producing more product to get back to equilibrium. So here's the Haber process. What will happen if more ammonia is added? So we're adding in ammonia here. Well, the reaction proceeds toward the reactants. The reaction proceeds towards the products. The speed of the forward and backward reaction increases. Or D, the reaction will not be affected at all. Well, obviously, we're adding in here, so it's going to shift to the left. That means that the reaction proceeds towards the reactants. All right, so a couple more things about Le Chatelier's principle, and then we'll look at the demo. If you add heat to an endothermic reaction, so heat is over here on the reactant side. Don't forget too that endothermic is delta H is positive, so they could put delta H next to the equation, and you have to know, if it says delta H is positive, I have to write in heat as a reactant. So if you add heat to endothermic, it's going to shift to the right and make more product. If you add heat to an exothermic reaction, over here, remember heat is a product. Remember delta H, of course, is going to be negative in this particular case if it's exothermic. So if I add heat, it's going to shift the other direction toward the reactants. Now, what if I took away heat? Just like before, if I took away heat and removed heat, it's going to want to replace the heat. So it would shift towards the side that has the heat. If you're removing something from that side, it's going to shift towards the side it's being removed from. So in this particular case, if you took away heat in the endothermic, it would shift towards the reactants to make more heat. In an exothermic, if you took away heat, it's going to shift towards the products to produce more heat in that particular case. But don't forget, sometimes you'll see delta H written in there. to tell you whether or not it's an exo or endothermic reaction, where to put the heat in the overall process. Now, pressure. Okay, here's that Haber process again. We have nitrogen plus hydrogen giving you ammonia gas. This one, you have to look at the number of moles of gas. So this is an understood one here, right? So that's 1 mole plus 3 moles. This is a total of 4 moles of gas on the reactant side. Over here, I have 2 moles of gas. Okay, so we need to know the number of moles of gas before I can decide which way it's going to go when it changes pressure. Increase in pressure is going to shift to the side with fewer moles. So in this case, we're going to shift to the right. Now, it wants to reestablish the same number of collisions with the walls of the container that was prior before equilibrium was disturbed. So in order to get back to that equilibrium pressure, it's going to shift to the side with the fewer moles in this case. If you decrease the pressure of a gas, the reaction is going to proceed to the side with more moles. So in that particular case, decreasing pressure, it would go to the left, and we would make more of our reactants over here to increase that pressure back to its equilibrium pressure that it once was to reestablish equilibrium. Now I want to point something else out about pressure here that you have to know. Pressure can also be stated in terms of Boyle's law. That gas law from a while ago. Boyle's law is pressure, volume, temperature, and moles stay constant. But if you increase pressure, volume decreases. Remember, this is the inverse relationship here. So sometimes they will phrase the pressure questions like, what happens if which way is it going to shift if I decrease the volume of the container? Well, if I decrease the volume of the container, that means pressure is going to increase. Then I would shift to the side with fewer moles. Now, if I increased the volume of the container, that means the pressure is going to decrease and the reaction would shift towards the side that had more moles of gas. So don't forget Boyle's law here. They can apply it and talk about the volume of the container and adjust the pressure based off of that fact. So don't forget to look at that as well. All right, so let me erase this here too. The other main point here that you need to know is if you have equal numbers of moles of gas, then moles, should say moles there will be no effect or no change in the equilibrium position. If you add pressure to a system where the gas moles are the same, there is no shift, no change. Okay? So remember, pressure changes only applies to gases because pressure is a measure of the collisions with the walls of the container, and that's what a gas can exert. Catalysts. Catalysts lower the activation energy in both directions. Remember, the hill goes down in our energy diagram, and the reaction can proceed faster. What you should know about adding a catalyst to an equilibrium reaction, what it will do is it will speed up the reaction and it will achieve equilibrium faster, but it doesn't affect the position of the reactants or products. It just speeds it up in both directions. So for Le Chatelier's principle, if you add a catalyst, there would be no shift in that case, just like there would be no shift if you have equal numbers of moles of gas on both sides of a reaction. Now for the demo. Now the video is right here, and you can watch the video and watch him pour in here, but I wanted to go through this particular one. It's similar to the one that you're going to do in your lab. With this cobalt complex, where a cobalt combines with 6 waters, has this positive here, and it's a pink color. So that would be the first test tube over here. Then you have this other cobalt complex with the 4 chlorides, and you have this -2. So this is they're called complex ions, but they're very pretty. They usually have lots of really good colors. So that would be the blue. And so then here, this would be when you have more equal amounts of both in the solution. Now, in this reaction, you can add chloride, and also here it says gaseous water, but it would just be liquid water that we would be adding. Now, first scenario here, you have test tube 1. You're going to add HCl here. So you kind of have to evaluate what are we really adding here. HCl is a strong acid. It's going to break apart into its ions. So it's going to be H plus and Cl minus. So really, what are we adding? We're adding in Cl minus here. So it's going to shift to the right. That means it should turn blue Okay, so here's the before, nice and pink, and here's it afterwards. Like I said, you can watch the guy do it if you want to. Now the next one in the demo is adding calcium chloride, which also, it's soluble. If you look at your solubility rules, calcium chloride in water, of course, breaks up into its ions, like so. So really, what are we adding? We're adding in more chloride. If you add in chloride, it's going to shift to the right, and it's going to be blue. So pay attention to number 2 here, because now we're looking at test tube 2. Yes, you add it in here. You see the pellets of the calcium chloride. Guess what? It's turning blue at the bottom here. When the stuff, and if you shook it up really well, the whole test tube would end up turning blue. All right, so now the next thing he does in his demo is he adds water to test tube 1. The test tube 1 is blue, as you can see right here. So he's going to be adding in some water. Now, adding in water is a liquid. It's a pure substance. So the water itself doesn't actually change the equilibrium. But what does it do? When you add water, you're diluting. So the concentrations of these guys all go down. They all decrease. Now what happens though is the amount of these concentrations decrease faster than this one. So it does end up shifting to the right. It's like these two are being removed at a higher amount than the concentration of the blue. So it's going to shift to the left. And as you can see, it turned back to the pink color. So it shift left towards the reactants because these guys were essentially, by decreasing the concentration, they were being removed at a faster rate. So it shifted to the left. All right, adding silver. So this is the hardest one probably of the bunch. Remember, silver nitrate. Nitrate is soluble, so it's going to form silver and nitrate ions in solution. Now, this is the thing, though, you have to know your solubility rules for. Silver plus chloride, guess what? Precipitates out into a solid. So if I'm adding silver to my system, it's going to combine with my chloride, essentially removing it from the system. Removes it, and therefore it's going to shift to the left and create more chloride. The other thing to notice here at the bottom, you see the white precipitate, but as you can see, the once blue over here is now turning more pink color. But you also do see the precipitate at the bottom, that is the silver chloride. Adding heat. So this is the easiest way to figure out if it's exo or endothermic. All right, I'm starting here. It's kind of pink. I'm adding heat. Guess what? It turned blue. So in order for it to turn blue, it has to shift to the right. That means the heat must be over here. It must be endothermic. So adding the heat shifted and made it turn blue. But now we can also do the opposite and test it and look at what removing heat does by putting it in an ice water bath. So in the ice bath, here's the blue to start with, okay? But over time, it shifts to the left, removing the heat, and it turned pink again. So once again, heat is over here, and this is endothermic. So you can tell that based on the fact that it had to shift towards the pink. To remove the heat, it's going to shift left towards the reactants. Now, this example also is in the notes where you can take a look and go through if you want to practice here. This is the Haber process again. Also showing here that this is exothermic because the heat's over here, so delta H has to be negative. So if I add in, if I add in hydrogen, it's going to shift towards the products. That means my nitrogen, though, which is also a reactant, is going to be consumed. So nitrogen is going to decrease in concentration, but that also means the ammonia is going to increase in concentration because we're shifting this way towards that direction. Okay, so that's that example. Now, if I add in, we're adding in over here, that means it's going to shift to the left. That means the nitrogen should increase. Both of these over here on the reaction side will increase. Okay, now removing. Now we're going to remove nitrogen over here, take it away. That means it's going to want to replace the nitrogen, so it's going to shift towards the reactants. That also means ammonia is going to decrease and the hydrogen is going to increase. So we're adding to this side, so hydrogen increases, ammonia is going to decrease. You kind of get the idea here. Removing hydrogen will do the same thing towards the reactants. That means nitrogen increases, ammonia is going to decrease if we're shifting to the left. Now, the last concentration example here is when we remove ammonia. So removing ammonia over here is going to shift it towards the products. And that means the other two, these two on the reactant side, will decrease. Now, because we're going to look at temperature, we have delta H is negative, heat is exothermic. If we increase over here, it's going to shift to the left, so towards the reactants. So that means the nitrogen is going to increase, the hydrogen should increase, but the ammonia over here on the product side will decrease. The opposite is true. If we remove heat from this side, it should go towards the products. That means the two reactants will decrease, both of these guys, and then of course the product, the ammonia over here, will increase. Now for the pressure. Don't forget to look at moles of gas for pressure. Once again, we have 4 moles of gas over here. Oops. Because we have 1 here plus 3, 4 moles of gas. On this side, we have 2 moles of gas. So if we increase the pressure, it's going to shift to the side with fewer moles towards the products. The 2 reactants decrease in terms of their concentration, and the ammonia is going to increase. Now, the opposite is true if we decrease the pressure. Okay, going to go to the side with more moles. So we would shift to the reactant side, and the reactants increase, and the product will decrease. Don't forget, too, that they could say increasing pressure by decreasing the volume here using Boyle's law, or increasing the volume using Boyle's law. There is this Bailing Beakers video that you're welcome to watch. It's about, I think 7 minutes. It's kind of cute. Gives a good simulation back and forth of the simulating equilibrium.